Hello everyone. I present today a platform for automated technical management services. So we use Ontology as well. This is a collaborative effort, so I'd like to acknowledge my co-authors, both from the Fraunhofer Institute for Building Physics, as well as the Technische Hochschule in Nürnberg in Germany. And we'd like to also acknowledge our financial funding. So both from the state of Bavaria and from the constituency from the European Union, so it's a previous project in the Horizon 2020 framework. So my presentation today is going to be, first I'd like to give an introduction and motivation for the topic. Then I'll present the platform architecture, where I'll first show how our Ontology-Based fault detection microservice can be implemented after, and then I'll show you the full-blown architecture, where we show how to integrate this in the platform architecture. I'll present some results for performing automated rule-based fault detection for error units, and in the end I'll give a conclusion. So first, for the introduction motivation, what is our motivation for the topic? Generally, it's about reducing the energy amount of buildings by improving building performance. And one technical building management services method is fault detection and diagnosis methods. There's a whole plethora of methods actually available. So I mentioned some here. And typically this is deployed by experts in building automation systems or energy management systems of building technical experts configure and deploy these methods manually to every specific task. And the challenge here, and this is something we are working on. So what we do is we use our Ontology-Based tool actually to perform this automated configuration and deployment. And this is some earlier paper we published last year, also at a conference. And how does this tool work for you for clarification? For you an overview, so we use dynamic data, monitoring data obtained through a building automation system or energy management system. We extract, transform, load this in some data storage database, and to configure automatically the mentioned analytics, we need static data of the building. So this can be, for example, building information modeling, which is also extracted, transformed, loaded into the stores as knowledge base, storing body attributes, describing actually the technical equipment, the building itself. And this information is used in the analytics tool, so for configuration deployment of this analytics, in the way that we first query the information for configuration from two sources, fixed queries for every analytic available. We join static dynamic data to evaluate if some fault is detected at some current state in time. And we report faults if faults are detected and generate results which can then be processed in some downstream application for reporting its course. So for large-scale deployment and enrolling this in, let's say, not only one building, but maybe thousands or hundred thousands, there's several requirements. So the first requirement already addressed our former work is automating the process, and the second requirement is that we like to have a platform where we can deploy this on a large scale, possibly then in the cloud. This is this work focusing on what I will present today. So first, the automated process I've shown just now, a bit more in detail on how to implement this as a microservice in a service-oriented architecture. So up here, what you can see, this is some rule from the APAR rule set. So this is one fault detection method where you use rule-based fault detection, evaluating a rule to determine some technical equipment is in fault state. So what this actually tells you is that this is a nominalized heating control signal of the heating valve in the heating coil of air handling unit. This is some parameters, and this is supply air set point temperature of this air handling unit or of the air handling unit, and the supply air temperature and also some parameter. So for configuring automating this process, we need to specifically know which data point in the building automation system actually is this certain supply air setting. So we implemented this as a microservice for 28 rules. So this method by Mr. Shine is composed of 28 rules, and it uses the ontology for configuration as well as historical data for the evaluation. And we look over the number of AHUs in our knowledge base. We determine the steady state if the current period of time is the steady state, as this is a requirement of the fault detection method. And then we execute these rules. So this can be packaged in one microservice, which can then be implemented in the service-oriented architecture of the platform and configured and combined with different other services and functionalities. So, to show you now the full-blown architecture, in the next slide. So this is the full-blown architecture. We model this, so we follow the service-oriented architecture paradigm, meaning that everything is a service and can be integrated with the enterprise service bus to be orchestrated. Into the enterprise service bus, we integrate different services for application execution. So this can be either installed on different machines or on one machine. So we may have one having the application container for our platform. We have a database cluster, some identity management, so this is authentication, and so forth, and microservice container, which can be microservices depending on your application. Communication can be either in the enterprise service bus or a certain external endpoint, or with scheduled data storage. And there's a dashboard server which you can use for visiting results and dashboards and presenting to the user or page. So how is this then integrated? Or the microservice I showed earlier, how we integrate this in this platform. But I'm specific here. So the microservice I just mentioned down here, it's an APAR microservice. And we have also the Ontology microservice, which holds the triple store. It can be accessed by some API. And the dispatcher microservice itself is only triggering the execution of the fault detection method. How this is running, is defined in a process which is defined in the enterprise service bus. And the message broker we use for actually allowing further execution of several processes. So this can be scalable for multiple number of AHUs, depending on the hardware we're using. So now some results from executing the platform. In a test case where we actually perform fault detection, rule-based fault detection of offline error data. So for everyone who's not familiar to too much familiar to error unit, typically have auto error temperature, auto error, which is set up to the system. You can either cool or heat it and supply it into the building, and return air can be either mixed with incoming auto error temperature or excess air, or can be released to exhaust. And what you can see here is that we analyzed data for 1 year, for one air handling unit, where we deploy the 28 rules in the APAR rule set, and we detect the fault in this specific case. So this is the temperature, so we have here mixer temperature, supply temperature, set point, and so forth. And first of all, we detect one fault here. But the second problem is to actually isolate the fault and determine the root cause of this fault. So the interpretation suggested by the APAR rule set is that this is caused by some stuck delta. For example, this mixing delta here. If we have a closer look, what we can see is that the auto temperature here goes well below or goes below 0 degrees Celsius. And typically in the air handling unit, you have some control strategy applied to avoid freezing of the coil at temperatures below -0 degrees Celsius. So this control logic most probably gets into place here, increases the temperature of the supply air and the mixing air temperature to prevent freezing of the heating and cooling coil. So taking a fault is one problem. Isolating it and isolating and identifying the root cause is a second problem. This will be addressed then also in future iterations. then, conclusion. So I presented some reference architecture for a platform, where we followed the service-oriented architecture paradigm to implement this. We showed the architecture integration of a fault detection microservice for rule-based fault detection. And we use ontology-based automated configuration for configuring actually this fault detection service in our use case. So this is kind of some downstream application where we reuse information from building information modeling for improving building operation. And so this is quite interesting to have this information available also from various stages in the life cycle of the building. Future research would like to extend, of course, the actual analytics we apply on our platform. So for now, it's only this rule-based fault detection, but we'd like to extend it also to other equipment in building, as well as other analytics. And of course, we'd like to also further test and validate our approach with more monitoring data. Thank you very much for attending.
Thank you, Georg. Are there any questions?